let me start recording. So we're doing a recording here on pages 4 through 6 of the 7-2 notes. Here's our example 6 worked out. So again, we let u equal 5x. So we have 3 over cosine squared u dx. 1 over cosine secant, so it becomes 3 secant squared u dx. Because u equals 5x, du dx is 5. If I move some things around, dx equals d over 5. Replace dx with d over 5, you have 3/5 times the integral, or 3/5 times tan u plus u, because the antiderivative of secant squared u is tan u. And then bring the 5x back in the fold. And then in green, you could check your work by doing the derivative. So that's a recap, just so you have a record of all that stuff. Let's now move on to, excuse me, example 7 and 8. Okay. Let's see here. And let me pull up my fill-out notes, because sometimes I get a little rusty with the nuances of these problems here. Okay. Okay, so in this case, we don't really have something for tangent squared, right? I don't see anything for tangent. I don't even see an answer for tangent either. So it's kind of weird. You can make it sine over cosine. And so what we're going to have to do is before, let me actually just as a text box actually. Before you integrate or do a u sub, try using a trig identity to rewrite the problem. So think of what you did in pre-calculus. So sometimes we need to do that. That's why on the summer packet, we had all that trig stuff and had some stuff on identities. I know it was a while ago, it was back in July, August. Now, for our test this weekend, don't worry about that. I'm not going to ask you to do that because I'm just getting you guys exposed to this again. But on the AP, they do expect you to know that. You are 100% expected to know your pre-cal stuff. Does anyone remember the identity for tangent squared from last year from pre-calculus? Let me jog your memory a little bit. Remember this identity? So I see some in the chat. Yeah, you're close. So Catherine's got a suggestion and we're definitely on the right track. So here's what we're gonna do. Hopefully remember this one. This is actually one of the more typical ones, and this makes sense because it follows Pythagorean theorem. Remember the unit circle, and then you have like a right triangle, right? And then you have like, A, B, C, right? A squared plus B squared equals C squared. But remember on the unit circle, C was 1, right? The horizontal leg was like a sine of your angle, and was like cosine of your angle. And that was like sine of your angle. And that's why that identity works the way it does. It's using Pythagorean theorem. It's also using the equation of a circle, which is x squared plus y squared equals 1 for a unit circle. The center is 0, 0, raised to 1. What if you divided all this by cosine squared? Then you would get tangent squared, because sine over cosine, that's another identity. Sine over cosine is tangent, plus 1 equals secant squared x. Or tangent squared x equals secant squared x minus 1. So that's what I'm going to do here. I am going to write this as secant squared of 5x minus 1 times dx. Now, I'm going to let u equal 5x. Therefore, du dx equals 5. And therefore, du equals 5 dx, or dx is du over 5. So now let me rewrite this. Secant squared u minus 1, dx is du over 5. So it's 1/5 of this integral. Secant squared u. I don't really need the parentheses around that u. I already know it's the input for the secant squared times du. Okay, now I could do the antiderivative of this. The antiderivative of that's not so bad. I'll do it kind of up here. 1/5 times parentheses is going to be tangent u minus u, and you have a plus c at the end. And then, of course, u is what, 5x, so it's 1/5 tan 5x minus 1/5 u, or 1/5 times 5x plus c. The 5's cancel, so it's 1/5 tan 5x minus x plus c. And by the way, the plus c, it's a constant, so you could do c over 5 if you wanted to, but it's a general constant, so don't worry about multiplying by 1/5. Just leave it as plus c. It's just kind of an arbitrary thing you do at the end. One question: why do we have to rewrite tan squared x? Oh, because we don't have an antiderivative for tan squared. I don't know what it is, so that's why. Yeah, that's why we rewrite it, because I don't know what the antiderivative of tan is. I mean, if you know what it is, please tell me. I don't know. So, well, I know I do now because I solved it, but I mean, there's no straight, like, simple antiderivative of tangent. So we have to use identities in that case. But again, I'm not going to expect notes for our test because we're just getting used to this kind of stuff here. And the more I think about it, I don't know if I'll quite finish off all these notes. So whatever I don't finish, I'll save till Monday. And I could reassess, I could assess that. You know, I mean, I already wrote the assessment, but things I'm doing right now are not going to be on the test, just things I should cover with you guys that will carry over to next week. Let's look at another one here. Let's look at example 8. And then perhaps we can revisit these other examples because I do want to give you guys a break also. Let's look at example 8 here. You have 2 tan 6x, right? Dx. Awesome. So what's going on here? Well, what we could do is, again, use an identity. You might remember tan theta equals sine theta over cos theta. Hopefully you guys remember that. So I'm going to put the 2 off to the left. I'm going to write this as sine 6x over cos 6x times dx. Okay. Now this is a little bit dicey. What you're going to do is let u, excuse me, equal cos 6x. How did I know that? Why not let u equal 6x? Why not let u equal sine 6x? Why did I let u equal cosine 6x? Well, first off, if you let u equal 6x, that gets us nowhere. Then you got sine u over cos u. I have no idea what to do with that. And by the way, you can't just say, oh, let's just do the antiderivative of sine and cosine separately and call it a day. No, that doesn't make any sense. You can't do the antiderivative of sine and cosine separately when there's a division. If there's a plus or minus, you could, but not multiplication or division. There's no quotient rule for antiderivatives, unfortunately. There's no product rule for antiderivatives, unfortunately. And we even mentioned that in the beginning of these notes here, to not do that. Actually, that was in the 7.1 notes, my bad. In the 7.1 notes, yeah, you can't just antidifferentiate product two functions and use like to do them separately and think you're good. Because if you did the derivative of that, you wouldn't get back to your original expression. So likewise, for a ratio of expressions that I'm seeing right here in example 8, when you have sine over cosine, nothing you can do about that. So I'm not going to let u equal 6x. It doesn't do anything for me. Then why not let u equal sine 6x? You could. You have u over cos 6x. You could. But let me take the derivative of this, and you'll see why I chose cos 6x. And then I'll give you a generalization after I'm done. So I'm going to let u equal cos 6x. So du dx, of course, is negative sine 6x. We know the derivatives of, actually negative 6. Let me take that back. Negative 6 times sine 6x. Because you got to do a chain rule also. So I know the derivative of cosine is negative sine, and I got to do a chain rule because there's 6x in the middle. So all the old stuff you got to know, right? Now, let me do a little rearranging. Let me move the negative 6 off to the left. Let me move the sine 6x. Sorry, let me move the dx to the right side. Now, do I see sine 6x dx in my expression? Absolutely you do. It becomes a very seamless substitution, right? So that's what I'm going to do next. Let me go back to blue. So I have 2 times the integral. And let me rewrite this as 1 over cosine 6x times sine 6x times dx. Okay. So same thing, I just push sine 6x dx off to the right. So 1 over cosine x is b, multiply that, same thing, right? Now I could do my substitution. 2 times the integral of 1 over u times d over negative 6. Because remember, sine 6x dx is d over negative 6. I have 2 over negative 6 becomes negative 1/3 times the integral of 1 over u du. What is the antiderivative of 1 over u? We've talked about this. It's natural log. That's why I let u equal the denominator. So the generalization is that if you have like polynomial expressions, yes, let u equal the polynomial expression of the highest exponent. If you have non-polynomials like trig or anything like that, typically let u equal the denominator. So you can use, so that you can use 1 over u du formula. And what is that going to be? Negative 1/3 times natural log of the absolute value of u, because you have the absolute value, plus c. So negative 1/3 times natural log of cos 6x. And you could take the derivative of that afterwards if you want to check see if you did this right, plus c. And that's negative 1/3, by the way. That's a little messy to see. And that's what we got. So if you did let u equal sine 6x, you wouldn't have been able to substitute for cos 6x dx quite as well as we did for this one. It wouldn't have worked for us. So typically you let u equal the denominator. That's what you want to do. These are things that we'll have to practice on Monday, because I do want to make sure I give enough time to review the other stuff. So the rest of these notes, pages 5 and 6, I will do on class on Monday. And that's good because we're not going to have any other homework, besides for you doing the test this weekend. So we could just kind of hit the ground running doing that on Monday. And then we'll do a worksheet on that stuff so you guys know. So I'll give you some textbook problems on that as well. The use of that, I do expect you to know, and again, it's only one question and kind of a part of another question. What I do expect you to know is what was in the video, kind of the more basic stuff, like on page 3 here. And of course, just doing antiderivatives in general, which you see on page 2 here. But a lot of that has been kind of somewhat reinforcing the earlier stuff too. So I'm not too concerned about that. But the stuff on page 4 is very new to you guys. I can't really fairly assess you on that this weekend. In pages 5 and 6, it's probably gonna take about 20 minutes to get through. And I don't think that's really best use of our time. So it's 10:01 right now. Let's take about a 9-minute break. Let's come back at 10:10. Let me stop the recording.